Good afternoon. I'm Barbara Matthew, and I'm welcoming you to the Monte Vista Grove Convocation Hour. Thank you for joining us. We'll begin with scripture today, and our scripture will be 1 Corinthians chapter 12, verses 4 through 6 and 24 through 27. There are different kinds of gifts, but the same Spirit distributes them. There are different kinds of service, but the same Lord. There are different kinds of working, but in all of them and in everyone, it is the same God at work. God has put the body together, giving greater honor to the parts that lacked it, so that there should be no division in the body, but that its parts should have equal concern for each other. If one part suffers, every part suffers with it. If one part is honored, every part rejoices with it. Now you are the body of Christ, and each one of you is a part of it. Thanks be to God for this message from the Apostle Paul. Let's pray together. May the one Spirit who brings us together be recognized as the source of our unity and the reason we use our varied and essential gifts to form a diverse but unified body in Christ. Help us, God, to recognize our differences strengthen the community and should never be seen nor used to weaken it. In your name we pray. Amen. I'm delighted to introduce to you John Denning, who is the Northrop Grumman Strategic Space Systems Azusa Site Hardware Engineering Director. That title takes more than one breath. John, his wonderful wife Lupe, with their 3 terrific offspring, have been longtime special friends of our family. Our son Rob and John met when they both worked at SEAL, a metallurgical company focused on failure analysis in the early 90s. Just days prior to the COVID shutdown in March 2020, John invited us to the El Segundo site of Northrop Grumman to see the enormous 5-layer sun shield, nearly the size of a tennis court, that will unfold and shield the James Webb Space Telescope from sunlight, allowing it to passively cool to frigid temperatures, like minus 388 degrees Fahrenheit. That's a chill. John can explain to us the necessity for such cold temperature, as well as the extraordinary expectations of the joint project of NASA, the Canadian Space Agency, and the European Space Agency. John, after a year of COVID confinement, we're ready to step beyond our current orbit. Please expand our vistas. Thank you.
Thank you very much, Barbara, and thank you so much for the warm welcome. I mentioned to Barbara that I had the James Webb Space Telescope behind me. Well, actually, I don't really have it. It's an image, but I like to think that it is behind me. It's such a big part of my life for so many years. I remember taking my daughters down to see a mock-up setup of James Webb when they were 5 and 7 years old, and they're now in their 20s, and now we're getting ready to launch the actual spacecraft this year, later in the October timeframe. So what we have for you is a presentation. I'm going to go ahead and share my screen here and give you an opportunity to see our this presentation here, and let's make sure that everybody can see it. Everybody see the presentation here?
See the telescope.
We see it? All right, outstanding. I also, just to fill everybody in a little bit more of how inspiring both Barbara and Jim have been in my life and in my family. One of my key takeaways that I've been with Northrop now for 27 years. And I've been in this industry for well over about 35 years now total. And I am going through a reinvention of myself. some of my classmates are actually joining me here too, because I also wanted to point out that you're never too old to educate yourself. Continuous education is such a key element, I think, of all of our lives. And I've elected to go back to school last year to pursue a master's from UC San Diego. And again, some of my classmates are here as well. So kind of stepping outside of my comfort zone, because I've seen others do that who had laid the ground before me, much like both Dr. Matthews. And so I'm so appreciative to what they've done for me and for my family. So with that, we're going to switch over and we're going to make this more about James Webb and the Space Telescope versus John. We've also known James Webb Space Telescope as also known as the Webb. So I'm going to refer to it here as the Webb from here on out. And let's go ahead and begin. All right.
The eye of the world now look into space. We need to be a part of it. We need to lead it.
We are a space-faring nation.
Oops, sorry. Give me one moment here. Let me adjust my volume. Hopefully this will help a little bit. All right, here we go. Let's go this again.
Pioneering is what we do. Today, we chart a new course that takes us beyond our wildest dreams. An exploration that requires a new craft. Currently under construction is a marvel of engineering that will reveal the dawn of time. And behold, the epic of creation. Where did we come from? Are we alone in the universe? The answers are on the horizon. The James Webb Space Telescope. America's next bold adventure.
Inspiring video. I'm wondering how many folks are ready to come out of retirement and help us complete the destination for the James Webb Space Telescope. It will be launching out of the French Guianas in the October timeframe of this year. So it's going to be packaged and it's going to go on its journey up the coast and through the Panama Canal, coming up here in the coming months. Right now, it's in a test phase. In doing some final testing, making sure everything works the way it's supposed to. Again, we get one shot at this. Unlike Hubble, we won't have the opportunity to go into space and make any tweaks to the Webb. So I have a rather large number in front of us in 13,500 million. And so many of you are probably wondering, well, John, why do you have this number here? But there is some significance to this number. That's how many years that we're going to be able to go back in time to actually see the first formation of galaxies and stars. So we actually probably could go back a little bit further than this, and you can see the timeline in billions of years. But to see past the 13 billion.5 million number, we would be in the dark ages, so we wouldn't be able to see anything anyways. But this is the power of this telescope, and we're going to go into a little more details. When people think of a telescope, typically they're thinking of optics, but this particular telescope is rather special because and we're going to go into some of the reasons of why that is. But it also has the ability to see in infrared, and then also it has a built-in spectrometer in there as well to be able to detect elements. So this is a pretty cool piece of technology. But we're gonna let's stick to what else this will do. So besides being able to look back in time, we're going to be looking at heat signatures, and we'll talk a little bit more about that as well. this is an opportunity for us also to replace, and actually it won't replace the Hubble right away, but it actually will be. It's a next generation Hubble. It's about 100 times more powerful than the Hubble spacecraft, and we're going to go in and do a few more comparisons of that later in this presentation as well. But we're really going to have the opportunity to step back in history, to review, to view how our universe was actually created. Astronomers and physicists alike are very excited, and also astrophysicists, folks are very excited about the technologies that the James Webb Space Telescope will be able to bring to everybody, to be able to see these formations and be able to see and point to areas that may actually have life. So we'll cover that. So we'll also be able to look at how stars and galaxies were actually formed and how they became to what they are today. And this is really, to be able to study the solar system will also give us that building blocks for life of where it might be. So this is exciting, to say the least. So another big number, 1,500,000. So again, what is the significance of this, John? Well, that's how far that James Webb, that the Webb telescope is gonna go out into space and actually be away from the Earth. It's gonna be so far away from the Earth that it's not gonna orbit the Earth. It's actually gonna go into an L2 environment where it's gonna orbit the sun. So, and you can see the comparison here. We talked a little bit about Hubble. Hubble is roughly about 570 kilometers away from Earth. And you can see the moon, where we had visited way back when during the Apollo era. You can see where it's roughly about 384,000 kilometers away. And we're going 1.5 million kilometers away, roughly about a million miles. And the other thing that's really cool about this too is that, and we'll cover this a little bit, Webb does not look like this when it launches. It's stowed. And Barbara mentioned that it's about the size of a tennis court. It's also 3 stories tall when it's fully deployed. We'll cover that, but it doesn't do that. It goes through roughly about 100 deployments, where Webb will end up being and looking like the Webb that you see there. And we'll cover that towards the tail end. It's a pretty cool piece of technology, not just to think what went into making it, but what it's going to take to actually get it out into that orbit and have it take its final shape. More numbers. Oops, sorry, let's go back to that. More numbers. Barbara had mentioned the 388 degrees Fahrenheit and 185 degrees Fahrenheit. And what that is, those are the temperature variations between the cold side, which is where the mirrors are, and the hot side, where you see this is where the electronics are. The sun shield here, the sun shield helps protect the optics and the infrared side to make sure that the James Webb Space Telescope is able to perform at its optimum abilities. And in order to do that, because it's also an infrared telescope, it needs to be super cold. And it's out there in space. And this sun shield, there are 5 layers. And really to talk about each one of these layers, and again, they're roughly, when they're fully deployed, it's roughly about the size of a tennis court, and it's 70 some odd feet. They're very thin. They're very thin layers of mylar, of film. How thin? Roughly about a millionth of an inch, which is actually thinner than a human hair. And there's 5 of these. And you think, wow, that's pretty thin. How do they not tear? We do all of that testing ahead of time, and we did have tears originally when we went and stretched it all out. In fact, when the Matthew family had the opportunity to come out and see the Webb, if I remember right, the sun shields were fully, I think they might have been fully deployed, but we can't keep it in that position for too long because it's very stressful on the actual spacecraft. We want to save that for when it's out in space. So but it actually acts as the sun shields actually act as almost like a sunscreen to prevent the that top side from getting hot. So that variation in temperature is really large. It's and one of the other elements of what the sun shields do, it's roughly about an SPF. You know, when you go to the store and you get SPF for your skin, you think, oh, I'm going to do an SPF 50. I'll do 100. You know, usually the higher the number, the better. What for the web, it's actually SPF 1 million. We love big numbers at Northrop and also for NASA. But that's really what's required in order for this space telescope to really work to its optimum ability. But we don't want to keep the electronic side that cold. The electronic side, again, this is where the sun facing, where it captures also sunlight. Remember, we also have solar panels there. We want them to actually collect sunlight in order for the electronics to work, the batteries to recharge, to make sure that we have our communications. You see that they're down here. Communication satellite, the communication antennas is really how we're also able to talk to the spacecraft, and then also for it to display images back and communicate back to the Earth and to the ground stations that we have. So imagine this piece of technology that has to function, and all of these materials and all of this electronics that have to function in an optimum condition and it's designed to last close to 10 years from what I understand. I might be wrong on that. I'll have to double check, but I do know that Hubble's been in existence for well over 20. And I know that most of our designs, they go for way longer than what we had originally built them for. So this is another piece of technology we expect to be able to do the same. Also, you see these, what we call the primary mirrors on top. It's very different from Hubble. And why is that? Hubble is one single mirror. Okay, it's roughly about 7.8 feet in diameter, but it's one mirror. The Webb is actually over 20. It's at 21 feet total when it's fully deployed. And you see that there are these there's individual hexagons, and there's 18 of them. The technology that was created for this, and they're made out of beryllium copper. In each one of those hexagons, when the beryllium copper is solid, it's roughly about 500 pounds. They're very, very heavy. So, and they're not gold like that. What Northrop and our subcontractors and NASA, what we've done is to collaborate. We have 18 of these hexagons that were manufactured, and what on the back side of this, they're ribbed, and there's quite a bit of removal of material. So much so to where it went from 500 pounds, and then we did a machining process to get them down to roughly about 46 pounds each. And they're still very rigid, and they're still, and they are aligned almost perfectly to where it is like a perfect mirror. It's so smooth that actually it's within I want to say it's somewhere in the neighborhood of about a millionth of an inch. So basically, you think about that. One of the stats that I had read that if you went through the entire United States, and if you had the same smoothness as each one of these mirrors, the highest point of the United States would be about 2 inches off the ground. So again, they are very smooth, and they're plated with gold. All of this 21 feet of the completed mirror, if they've been plated with roughly about the size of a golf ball of gold. So again, it's within the millionths of an inch, and they're so smooth and so perfect when they align that it appears to be a single mirror. And again, we'll kind of explain why that is, to where we chose to use this design versus a Hubble type design where it was one single mirror. It'll make a little bit more sense later. The secondary mirror here, basically what it does is it collects the image from what's bouncing off of this entire surface here. Collects here, this is a collector, comes back in here, and this is a sensor. It collects, again, data from what it's seeing out in space. But it's pretty cool technology when you're thinking of all these things. This is definitely a first. But then also maybe another question that you might have is you might be thinking, well, why are we putting something so far out in space? Why not keep it a little bit closer? And part of the reason why we do that is because the further out we go, the less interference that we have from things like the Earth that might help distort images. Further out like this, you don't have that. When you, for ground station type telescopes, they typically you don't get the same crisp images that you get from telescopes out in space. And again, part of that, especially on the from a mirror and an optic standpoint, is because we're seeing the waves of the radiation of the Earth, the magnetic fields. If you notice, when you look up in the sky, people will see stars that twinkle, but in space they don't do that. They're continuous light. So and again, it's the optic effect of the radiation fields and also of the magnetic fields from Earth. So let's go ahead and move on. We talked a little bit about the sun shields and the 5 layers. Each one of these needs to deploy. We'll talk about that a little bit further here as well. But again, it helps protect the optics, and it also helps protect our ability to perform in the infrared. And when we talk about the infrared, why do we want to do that? We're going to show some images here because, and I didn't do a good job yet of explaining how this is a time machine, of how we go back in time. And really what we're doing is we're looking at residual heat signatures that have remained in space from the Big Bang, from the first formation of those stars and solar systems. Those heat signatures are still there. When we're talking about, when we even look up in the sky and we see the stars, when we're talking about the speed of light for those images to come back to Earth, it takes years for that to come back. But what Webb does is that, remember, beyond the optics, it's also using the infrared to be able to see some of these formations. And beyond the formations, it also has the ability to see in infrared to see past things. So in a certain frequency, and we're going to cover that in a moment here as well, you'll have the ability to see through dust clouds and to see through formations that had formed from way back millions of years ago, and even billions of years ago, where the heat signatures are still there, but we're going to be able to see through some of those dust clouds to actually see what's behind that, to see some of the stars and the formations beyond that. The best way to kind of think about that is we also have technology that we use here at Northrop, to where we have microwave technology and RF technology, to where for weather satellites, for example, when we want to be able to see, we have the ability to actually see through clouds and actually see what the ground layer is, but that's in certain frequencies. So we're going to cover a little bit more about that too. So there's some really cool stuff that we have the ability to do and that we continue to do. All right. So we talked, I covered a little bit about the infrared, but let's go into this a little bit more in detail of some of the materials that visible light can't see through. We're going to be able to do that with James Webb, and it's going to be much more crisp even than Hubble. Again, you see that you do a comparison here with the Hubble Space Telescope, which is the HST, with the frequency band that it's in versus which ultraviolet versus infrared. So we're going to be able to see much more detail with the James Webb Space Telescope versus something like Hubble, or whether and I'm not as familiar with these two satellite systems here in Swift and RXTX, but you can see that they have a certain band frequency that they work in to be able to see out into space, into the universe. And then also you see we covered a little bit about microwave technology. Microwave technology, I know also, besides being able to cook your food, right? We actually use microwave technology to actually see in heavily clouded areas, and we talked very briefly about that. Those are some of the other what we call sensors that we manufacture here at the Azusa facility for Northrop Grumman, which is also by the way, it's a legacy Aerojet facility here. Strong history back to Caltech and also to Dr. Theodor von Karman, who was not only a Caltech professor and professor along with Albert Einstein, but one of the greatest physicists that has ever lived. We have a long legacy history between Caltech and also this campus. One of the claims to fame for Theodor von Karman was the JATOs, which is jet assisted takeoff. That was very big here for a period of time to get a little extra boost for planes to get up in the air that are very heavy. So going back here to the Webb, again, with our infrared camera, again, we'll see the heat signatures. So this is one of the things, this is kind of an example, sorry about that, bear with me here. One of the things that we would, an example that we'll be able to see, I have some at the back end of this as well, to where what you can actually see visually versus what you can see with the infrared camera. It's kind of think of the way a snake actually sees as well. You see the heat signatures. It would be irrelevant to a snake or anybody that's looking in the infrared band to see whether they are, whether their hand is in a bag or not. Visually, you'd see that their hand is in a bag, but through infrared, you'll see everything as though that bag didn't exist, to see right through it. And the infrared light that can be seen through the thick smoke and fog, we'll show an image, a couple of images of what that actually means. So this is a good example of visible light versus what you would see in infrared. It's almost no comparison. And why is it that you see, again, you see just a couple of the bright stars that are poking through here, but it's really difficult to believe that you have millions of stars beyond that. And you wouldn't see that if you were looking straight in a visible light. You would only see that if you were to be able to use an infrared. And some of the images that you've seen from Hubble, they display this very nicely. So this will be also an opportunity for us with the Webb to be able to see even better and see things, and again, highlight different areas that we can actually point to in the universe, and be able to see some of the planets and the moons that might be hitting some of these suns or these stars as well. Really exciting to be able to think that the amount of technology that we're utilizing and what we're going to be able to do with it, and what we're going to be able to see and find. So these pillars of creation, again, you see the what's an infrared, what's not. Again, let's see if there's anything else here that we covered. I think we covered everything on this. So let me go ahead and move forward. All right. So we talked a little bit too about why we couldn't have a 21-foot mirror. It's because it wouldn't fit in the cone of a rocket, at least not the ones that we have and we built to date. And you see this tennis court size 3-story piece of technology in the Webb in this nose cone of a rocket. And here, this is an Ariane rocket that it's part of the European Space Agency. This is what you see here as ESA, which is the European Space Agency. Also, again, the NASA collaboration. I know Barbara mentioned the Canadian Space Agency as well. They're also involved. But to give you kind of an idea of scale, you see these people down here on the bottom, and you can see how large this actual Ariane rocket is, and how large, again, the Webb telescope is. But again, in this stowed state, it's almost like, as they described it, as like a transformer that's going to kind of unfold with time. And when it does unfold, we'll cover a little bit about this in the deployment sequence. It's very violent. And what is meant by that? There's like little mini explosions that go on that actually blow apart these holding mechanisms. In many cases, they're bolts or they're nuts, and basically they need to be strong enough to hold everything in place when it goes through a launch, but they also have to be weak enough to where when we go through and actually go through the explosions to break them apart, that everything deploys the way that it's meant to deploy. There's so much, again, when you think about it, this has been about 20 years in the making. It's a one of a kind. And all of the engineering that has gone into this, the collaboration that's gone through multi-nations and multi-subcontractors is just immense. And it's a beautiful piece of technology that's going to be used for additional discovery of humanity. I'm just so excited about this, but also so proud to also be part of this, both from a materials standpoint and from a quality standpoint, and now also from a hardware standpoint of everything that's gone in and what we've done here for the for Webb. So let's see. Okay, so here's the deployment sequence. We're gonna let this play. So you can see it going out into space, and pay attention to the hours and the days of how long it's going to take for it to get into its final orbit, and how many different things need to happen in order for it to become what we've seen earlier in the actual final spacecraft view. Doesn't really look like one now, right? It looks kind of like a rectangular box with some hexagons poking out on the side. So maybe some of you recognize this. This is a sun shield, but you see that it's pretty flat. It's like, where's the rest of it? So we're past the moon. There are membranes for the sun shield that are unfolding. It's capped on, by the way, for anybody who's interested. The other thing that we had to do here too is make sure that we minimize any form of contamination. Any piece of fiber, any piece of fabric, of anything that potentially could get on top of the optics or even on the sun shield would take away from the performance of the actual spacecraft and telescope. So we're getting close to where we need to be. Got half of the telescope, and there we go. The other half is connecting. So mid-course correction, basically what that means is that there's little thrusters around the spacecraft that will help position it. And then it's going to go into that L2 orbit. And that's pretty much our deployment sequence. So that it's roughly, and you can see, I think it's somewhere in the neighborhood of about, it's close to 100 deployments. And it takes, you see, about 29 days, if I remember right, of how long it takes to get to its final state and out into its final orbit. It's going to take some time. So after you hear and read about the launch of the Webb, be patient, because it's going to take a little bit of time to get everything to unfold, and then they'll test it to make sure that it's fully operational. All right. So this is what I have behind me, a version of it, and you see that these folks here from Northrop are in their what we call bunny suits, but it's all, remember I mentioned about the contamination control aspect of things. It's a clean room environment. You have to make sure that you treat this with the utmost with care. We can't have anything, like I said, that gets on either the sun shields or the optics. We got to keep them pristine. Because remember, also when it goes out into space, it's in a vacuum environment too. So it really isn't. It's really not designed to pick up a foreign material. It should, again, in that environment, it should stay relatively stable and clear of debris. So let's see here. So we have the questions aspect, but before I actually start fielding questions here too, we talked a little bit about Webb and how big it is and the comparison to Hubble. So here mentioned that Hubble is roughly about, I didn't mention this, but I was only talking about the diameter of the mirror being about a little over 7 feet. But the length of Hubble is roughly about 44 feet, which is about the size of a school bus. But you see Webb is 72 feet long, which is comparable to a tennis court, and that's in that fully deployed state. And then also, again, this mirror is humongous. You can see that it would not have fit in a traditional cone. So again, we had to develop that technology to make sure that when it unfolded, that it lined up perfectly. Because if it didn't line up perfectly, it wouldn't be a true mirror. It would distort the images. We talked a little bit about the sun shield that already. So again, it's kind of a cool thing. And then one last thing here that I wanted to show is, again, the ability to see in infrared. So, and again, it is a type of light that our eyes really aren't that sensitive to be able to see. Again, this is much like how a snake would see in their ways through infrared eyes. But again, it's just kind of a neat thing to actually see something that you might recognize via infrared light. So that pretty much concludes what I have. So I'm going to go back here into the question part, and let's see what you might have for me. Hopefully I spurred some interest in people wanting to know a little bit more about the James Webb Space Telescope, or Webb.
All right, you guys have the option to unmute yourselves now. You can always also type your questions in the chat box, and I'm going to launch the polling.
And don't be shy, it's okay. You can ask me anything. I may not know all the answers, but I will. Here's the other thing, my commitment back to this group. Whatever I don't know, I will find out. And I can also guarantee that if nobody asks questions, I'm sure my classmates and also Northrop employees will pepper me with questions as well. So I would enjoy any questions that you might have.
I have a question, if I can be heard.
Yes, sir. And did you go by William or Bill?
I'm Bill.
Bill, outstanding.
John, I'm stunned and so excited with your presentation. And I think, honestly, there were so many questions that I could ask. But let me just begin with one about the manufacturing process. For instance, the mirrors manufactured here where there's gravity. What kind of, how are you compensating in the manufacturing process for the Webb for our pull of gravity as compared to what it's going to be when it's deployed?
You know, that's a really good question. And I don't know that I've actually given much thought, but I'll tell you what. Let me explain a little bit about the process itself. There's quite a bit of material removal process that you need, and beryllium is also really kind of a nasty material in order to work with because it's carcinogenic. So much of when that is done in the material removal process. Is done also in some form of a clean room type environment. It's not really a clean room, but it's a very restricted environment. So to make sure that people aren't breathing in the particles that come off from that removal process. And when we're talking about a Webb, I really wish that I would have included some photos so you can actually see to appreciate how thin that they actually get the material. And again, the part of the reason why beryllium was selected in the first place was because of the rigid properties and because of the fact that when it's out in space and when it's on that cold side, that it's not going to restrict that much and hold its form, especially when it's in alignment with those 18 other single mirrors that form that huge 21-foot mirror. But we obviously cannot, we have tested, and I'll tell you, we've taken it down to temp. That's one of the things I think that people don't truly understand about why products that go into space, especially this far out into space, why it costs so much. It's the testing that we do that to validate that the electronics work, or that the actual material selection, that everything works the way it's supposed to work. But to my knowledge, I know that that there are some chambers, very few, and I'm not sure if they were at NASA, and they might have been. We did quite a bit of work between the Maryland facility in Goddard, also Johnson facility in Texas, and then also our facility at Redondo Beach. Between the three, we've had some pretty strong labs that we were able to emulate some of the actual low temperatures. I think that the thermal vac temperatures that we did, that was done at Johnson. So they would have emulated the extreme temperatures from one to the other. But it wasn't part of the manufacturing process. It was more that final test. I think that we also relied quite a bit on calculations that the engineers had done, and also model-based engineering that would project that, hey, when these all align, that everything will work. It's not going to change its configuration to the point to where it's not going to function. So it was a little bit of a combination of theory plus test. But the manufacturing process itself, I don't believe we did anything special other than the design aspect of things to be able to hog away roughly about 450 pounds of material and still maintain the rigidity that was required in order for that to work. Bill, I'm disappointed in my answer. I wish I would have given you something a little bit more specific to your question, but I don't know that we did anything special, to be really honest with you, from a manufacturing standpoint.
What about the transmission from the Webb back to Earth? Any comments about that, please?
So that's also a good one too. I think that we've most recently have seen transmissions that are going from Mars to, with the latest rover back into Earth. So we're not quite that far out, but basically it's antenna technology, and there's certain wavelengths that actually that we have with our antennas that have the ability to transmit and then receive on ground stations and then transmit back. I know that there's huge delays. I don't know the exact frequencies that we stay in as far as bandwidth goes, but I do know that I was involved from a material standpoint quite a bit in the antennas for some of the material selections that were done, the integrity of the antennas to make sure that they would actually work the way that they're designed. But the actual frequencies and the functionality specifics, I don't know that. I know that you can learn more about that, Bill, too, on the NASA websites. And I will tell you, if you have an interest in anything in particular like that, and you really want to know, I'll definitely align you with the right expertise, because there are some brilliant people that have worked this. I'm not one of them. I'm basically a manager, so I have the ability to call on the right technical expertise to come in and address questions like that, because they're very important, and we definitely need to understand how this is gonna function. So again, I wish I could give you a better answer to some of the specifics, but I can find out if you'd like to know.
Well, I just want to say what you've given us has been intensely interesting, and I pray for the success of this mission. I just think the information that's going to come back will be astounding, and I'm so excited. So just want to applaud the work that you are doing, and oh my, thank you for your presentation.
Thank you. You reminded me of one other thing that I wanted to cover here too. I talked a little bit about the spectroscopy element of the Webb, but really what that means is that it also has the ability through light to actually be able to see elements that are on a planet or a star. So this actually gives us the ability to see water, and whether the atmospheres that we're seeing are conducive to life. And that's the other thing. It's not like the Webb is going to be able to see Martians or aliens out in space. That's not what it's designed for. It's really more designed to not only see the inception of the universe, but in addition to that, to find those areas that might be out there that might actually have the ability to sustain life. And that to me is also very, very exciting, to have that prospect, that again, that we're continuing our human discovery. It's super exciting to know that that's right around the corner. So again, Bill, thank you so much for your questions.
Thank you.
Who else might have, please.
John, we have several in the chat. The first
Very
one
good.
is, there are so many moving parts. How much redundancy is built in?
Oh, that's a great question. So again, redundancy also costs a lot of money too. So there's a tremendous amount of weight too that we've been trying to salvage and save. So in certain areas there is no redundancy. It's a one-time thing. So the deployment is a good example of that. You get one shot of that. So when you see those arms that are deploying out for the sun shields, there is no redundancy. That's a one-time deal. But for the electronics and some of the transmissions and receiving, we do have built-in redundancy in some areas there. Also for power in the way that we've designed some of our systems. In case one system does fail, we do have backup systems. But it's very strategic in how we have done that. You know, I know nobody asked about the weight yet, but I do want to kind of cover that too. The Webb is roughly about 14,000 pounds, which, believe it or not, based on the size, it's about half the weight as Hubble. So that what I'm really also saying is that there was a lot of newer technologies. There's composite technology that was developed and utilized for Webb. We also talked a little bit about about the sun shields and how thin they are. But again, it's but when it comes to weight, the more weight you have, the harder it is to get up, the more expensive it is to get up, especially into that L2 orbit that we're talking about. So the redundancy, it's there in certain areas, but we couldn't make it redundant everywhere. It's a great question. Thank you.
Here's another one. Is a solar orbit also chosen over an Earth orbit because there is less chance of debris?
You know, that's a great question, because I was thinking about that a lot. I had asked that question so many times about even when it's out where it's at. How do we know that it's not going to see some meteor shower? And basically, we try to have the ability to steer away from those, from things like that. We do have sensors that are on board. But yeah, that is a great question. That is, I think there's a combination. You're going to get less debris when you're out that far out. Orbiting the sun. Nowadays, I don't know if people have paid attention to how cluttered our own atmosphere and orbits have been, especially in the low Earth orbit, which is also known as the Leo orbit. Nowadays, you'll see literally hundreds of mini satellites that are deploying these days, and then also debris from satellites that have broken apart with time. There's just so much stuff that's up there. Very difficult to dodge all of that. So that is a very astute question and comment. I don't know 100% that's why, but from a logical standpoint, I think that has a lot to do with it. But I also know that they wanted to get out that far to also take advantage of the maximum capability of the Space Telescope itself. So I think it might have been a combination of both.
We have a couple more in the chat, but I'd like to leave room for live questions too. Anyone else have any? Okay, our next one in the chat then is, are other countries involved in this, or are other countries working on their own kind of web projects?
That's also a great question. Now, this is definitely a universal type of consortium. So when we're talking about the European nations, typically they're U.S. friendly type countries. I don't know what China or Russia might be doing as far as specific telescope type activities. I can tell you that this was, like I said, over 20 years in the making. It takes a lot of commitment. The engineering was super intense. to do, and it did, having that collaborative effort between Canada, between the European Space Agency, with NASA, with us, has been tremendous. Also with our subs. Our subs, our subcontracts and suppliers, they span across not only the continental United States, but across the globe. So it truly is a global effort. But I, typically speaking, for events like this, basically what this is that it's really focused more, again, towards the US friendly type countries as well. So, but yes, it was a joint effort.
I think one of your colleagues may have chimed in here. Antonio says 14 countries are providing hardware components to build the James Webb Space Telescope. Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, Spain, Sweden, Switzerland, and the United Kingdom and the United States. I think he also alphabetized those. Wow.
Thanks, Antonio. You know, but I also wanted to highlight, those are 14 countries, right? But within those countries, we also have a tremendous amount of supply base that goes along with that. So that represents the countries, but I know that there's thousands of suppliers that actually helped out in some form or another in order to provide materials, to do some of the special processes, to provide the components, and much of this was assembled at the Redondo Beach facility here at Space Park, which is a legacy TRW facility. But again, a lot of the testing was done elsewhere, and pieces came together in some that was provided by these multiple nations that we were able to integrate in and to find to create this massive piece of technology that, again, will be flying. Keep our fingers crossed by the October timeframe. Thanks again, Antonio. What other questions, Lindsay, do you see?
Let's see. There was an initial focus issue with the Hubble. If such should occur with Webb, can it be corrected?
No, that's it. No, that's a great astute comment too. Yeah, that was very disappointing from what I understand. When Hubble first launched, it couldn't get a crisp image, and apparently one of the prisms was installed backwards. So there was actually a space shuttle mission that actually went out to visit the Hubble, and where they actually went out and changed out a panel and corrected and put in the right prism in the right orientation to get it to work. And then all of a sudden, voila, you're able to get these crisp images. But you know, I don't think any taxpayer wants to see literally billions of dollars of investment go down the tube and not get anything for it. So no, we're so far out in space. This is a one-time thing. But I can assure you too, there's been so much engineering and so much test work that has gone into this that that we're very comfortable and confident that we'll get it right first time. So, but we have one chance at this.
Okay, audience, I'd like to remind you to vote in the poll if you have not, please. And I have another question in the chat. What was used from the IRAS satellite? IRAS. I don't know if I'm supposed to pronounce the letters or not.
So specific, I'm not as familiar with IRAS. I know the acronym, and I do know that I'm familiar with the actual spacecraft itself. But I can tell you that from a NASA perspective, what NASA tends to do too in its designs, they do try to capitalize on what they've learned previously. So I'm sure that there are elements there that are being applied. I'm wondering also if IRAS is the IR is infrared, so which means that technology would definitely be applied. Infrared in space telescopes it's not unique to Webb. I think the power of this particular one, with the elements of everything else in the mirror, is something that's a first. But I'm certain that that NASA and Northrop and the space agencies that were involved here are going to try to capitalize on pre-existing technologies to the best of their ability. But there's a lot of firsts for this one too. So I'm sorry, I can't give a more definitive answer, but again, I'd be happy to field that further if my answers aren't satisfactory.
Do we have any spoken questions? All right, one more in the chat. Can the Webb be repositioned from the planned site?
Yes, that's a great question. And yes, it can. In fact, that's what it's designed to do too. And I mentioned about the mini thrusters, that those are positioning thrusters too. So it will have the ability to steer the scope. So if we wanted to see a planet that, let's say um, it's positioned to look at a certain galaxy or a certain planet or star, it can easily rotate around to be able to see something else that might be of interest. And what I also understand, I know that there's been some recent discoveries, I think, with Hubble that where Hubble had identified a planet that might be able to sustain life. I have a feeling that that might be one of the first things that the Webb will look at as well. But again, that's just one element of the galaxy, right? You want to be able to look at everything, and that's also one of the things that I think Bill had asked earlier about the antenna and the communication ability. That's what we need to do in order to be able to position. You have to send those signals up to be able to position the satellite in the right way. It's going to respond to the commands that we send from the ground. So yes, we'll definitely be able to do that. That it's designed for that.
All right, any final questions? I have none.
So Lindsay, what I'll do is I'll make sure that this presentation is available to all. I know that the size was really large. So again, I'm sorry I didn't get that to you beforehand. And if anybody can think of anything that they're interested about, you can also track the Webb at the NASA, the main NASA site. And then also you'll have the ability to, if you really want to know, you can reach out still through Lindsay to me. And again, I'll do my best to try to align you to the right people. For those that might have family that work at Northrop, what I would recommend is you're going to have a small window that if you really want to see it, the way that it looks behind me right now. Let's see, I'll move over to the side here. There's a display window. There's 2 floors that you can actually see it. So it's going to be available for viewing for the public, but you need to be escorted in by a Northrop employee. You please take advantage of it. Come out and see this amazing piece of technology, and to know that it's going to be flying in space for many, many years to come, and to help with human discovery. It's take advantage of that opportunity if you get to. You just can't take a camera in, unfortunately. So we are still a government defense contractor too, so we don't allow cameras in our facilities. But other than that, you get a chance to see it firsthand.
Well, John, I'm going to jump in here and just say thank you for this experience today. It's so far over my head, but we really enjoyed the tour that you were able to get us into. So I would certainly encourage anyone who has that opportunity to take advantage of it. And
Barbara, thank you so much for having me out. I really the opportunity to speak to the group and to you and to Lindsay. I'm so honored. Thank you so much for having me out. Hopefully there are elements of this presentation that got people excited and knowing about what's going to be happening right around the corner. And again, so much I've seen so many people that have devoted so much of themselves in that engineering mindset, and the astrophysicists and these mechanical engineers and thermal engineers and structural engineers and electrical engineers that have all come together to help create this modern piece of technology is just mind-blowing to me as well. So again, I'm so excited to be able to see the fruits of its labor here coming up within the next 6 months or so.
well, your words fit so well with the scripture we had. So many gifts that come together to make a body, and in this case, the creation of this extraordinary telescope is human collaboration, and that is a beautiful thing. So thank you so much. For so many of us who've been relatively housebound, you've really transported us to an entirely new space today, and we're so grateful, John. So many
Thank you.
thanks.
And hopefully we'll get a chance to meet in person again with the entire group. So
Yes.
looking forward to that day.
Maybe when it's launched or before it's launched in October, you'll join us again. Thank you.
Thank you.
If I could just say a few words about next week's convocation. You'll meet our new resident, Reverend Catherine Hughes, who began her residency in C70 the day after Thanksgiving and is now happily in her own place of D98. And also we'll have an interview of Sandra Mader, president of the Monte Vista Grove Homes Board of Trustees, by Libby Patterson. And Sandra is well known to so many of us as she served as a faithful member of our Board of Trustees, which she now chairs. So join us to know more about these two accomplished women we're so fortunate to have in our midst. Thank you. Thank you for joining us today.